Optimal allocation of multi-renewable DG integrated with distribution network reconfiguration based on MOFF approach. Abstract. A novel approach is anticipated in this paper for optimal allocation and sizing of multi-renewable DG with reconfiguration based on multi-objective function approach using PSO technique. The objectives of reduction of active power loss, reactive power loss and voltage deviation, also considering reliability enhancement of the system. The proposed work is carried out using MATLAB. The result of the proposed method has been studied and validated on IEEE 33 bus radial distribution system. The proposed approach is considered with different cases, which includes optimal DG planning with reconfiguration based on the multi-objective function. Keyword: distributed generation, optimal planning, network reconfiguration, particle swarm optimization technique, PSO. 1. Introduction. The distribution system is an important part of an electric power system. As stated in 1, the capital investment in the distribution system constitutes a significant portion of the total amount spent in the entire power system. Due to the recent market deregulation, this portion may become even larger. Furthermore, since the distribution systems operate at the low voltage levels, the losses are usually higher compared to those in other parts of the system. Thus, the distribution system rates high in economic importance, which makes careful planning and design most worthwhile. DG placement in distribution system network can diminish numerous problems to a great degree, like reduction in power loss, improvement in voltage profile, drop in power demand, power supply to the consumer with improved quality, cost minimization at peak operation, enhanced safety and reliability, reduced greenhouse gas emission, grid strengthening and so on. In 1, by using mixed integer nonlinear programming, MINELP, based optimization method, the optimal planning of DGS are found and cited in the 33 and 69 bus distribution system network to decrease the losses and improve the voltage profile. Teng et al. 3 and Diaz et al. 4 presented load flow analysis, which is used in the presented work. Many researchers have stated that different optimizing techniques 5 to 11 are available for the determination of optimal planning of renewable DGS, which can maintain the performance, operational, economical and reliability issues. The genetic algorithm optimization technique is given in 5 to 7, while the particle swarm optimization technique is given in 8 to 10 are used for distribution system planning. In 11 it is discussed that what kind of commonly used technologies are available to harvest the energy by using DGS near to the consumption place and their different type of module size. Prakash et al. 12 presented a comparable study for the optimal placement of DG in IEEE 69 bus radial distribution system, RDS, between PSO and BAT algorithm, BA. Sadiasday et al. 13 presented a work based on reconfiguration with the objective of loss and reliability indices minimization. In 14, depending on the injected power, DGS are characterized as 4 types. Reddy et al. 17 proposed a work, namely reconfiguration of IEEE 33 and 69 BUS RDS using PSO. The DG planning with reconfiguration is a complex target to achieve with a fitness function which issuing multi-objective function constitutes nonlinear constraints. In the presented work, the PSO technique is used in order to evaluate the optimal planning of multi-renewable distributed generator with reconfiguration. In the used methodology, the radial property of the distribution system network is always maintained for load flow study, LFS. Newton-Raphson method is used for load flow study, which is more superior to basic load flow method for radial systems. The proposed work is organized in different sections as follows. The section 1 contains introduction methodology is given in section 2, in section 3 optimization technique is explained, section 4 is about result and discussion, and section 5 is about conclusion. The different cases of proposed work areas follows. 2. Methodology based on MOFF. Multi-objective based fitness function formulation. In this section, advanced multi-objective fitness function, MOFF, is introduced, which consists of distinct system performance and reliability assessment parameter. This novel fitness function based problem is utilized for the optimal planning of multi-renewable DG with reconfiguration by using PSO technique for different cases. MOFF equals C1 APLI plus C2 vol DI plus C3 RPLI plus C4 RLI, where C1, C2, C3, and C4, having the values 0.40, 0.20, 0.25, and 0.15 respectively, are weight factors which define how much weight we have given to each variable system indices based on priority. APLI active power loss index, vol DI voltage deviation index, RL reliability index. Basis 10. APLI, vol DI, RPLI, and RLI are active power loss index, voltage deviation index, reactive power loss index, and reliability index respectively. In the fitness function we have given priorities to all the important factors that will make our distribution system more efficient and reliable. In the said work with the proposed methodology, active power loss, APL, reactive power loss, RPL, of the system is reduced as shown in Table I while the voltage profile and reliability of the system has improved as presented in Table 2. Let us assume that an N-bus power system contains a total number of NP-PQ buses while the number of PV, generator, buses be NG such that N equals NP plus NG plus 1. Bus 1 is assumed to be the slack bus. The approach to Newton-Raphson load flow is similar to that of solving a system of nonlinear equations using the Newton-Raphson method. At each iteration we have to form a Jacobian matrix and solve for the corrections from an equation of the type given. For the load flow problem, this equation is of the form 3 optimization technique. The first ever PSO technique was stated by Kennedy and Eberhard in 1995-9. PSO is a population-based optimization technique 8-9. In PSO, in its search area every swarm follows a stated inertia and velocity by associated iterations. Based on the swarm last local best understanding and the past best understanding in its neighborhood the speed and way of the velocity are in tune. The characteristics of the swarm are to fly towards a promising area in the search area. PSO counts each individual's movement in the complete search area with a specific stated velocity which is updated according to its local movement understanding and its colleague's movement understanding A10. In Fig 1 the PSO technique algorithm flowchart has shown. In PSO the population of particles are initializes randomly and the corresponding updates in the particle's position is totally based upon the local best and neighbor best experience 10. At every iteration updated new values of the velocity are the deciding factor for updated new value of the population. Swarm updated population is the sum of population of previous iteration and the velocity of current iteration in the next iteration. Suppose total population is p and respective velocity is v. The velocity and population for ith iteration is v, I plus 1, and x, I plus 1, respectively. Similarly v and x are the velocity and population for previous iteration. These two equations are given in order to update the values of velocity and population for ith iteration are given as 6, 8. For results and discussion. In case 1, base case is considered without reconfiguration and DG, and obtained results are active power loss, APL, as 0.2027 pu, reactive power loss, RPL, as 0.1351 pu and maximum voltage deviation, volt, of the system as 0.0869 p.u with respect to reference voltage. While in case 2, the standard IEEE 33 bus roads with only reconfiguration is considered by maintaining the radiality of the system. The observed results are APL as 0.1020066672 pu, RPL as 0.06595468 pu and maximum volt of system as 0.040345 pu respectively with respect to base case as shown in Table 1 and 2. In the same fashion when we have implemented single DG by using PSO technique in case 3, APL, RPL, and volt is reduced by 48.69%, 44.60%, and 44.48% respectively as shown in below 3 table with respect to case 1. In case 4 we have considered multi-DG by using PSO technique where we got APL reduction 59.71%, RPL reduction 58.62%, volt decrease by 69.96%, and hence the reliability is increased to 96.39% as shown in Table 2. Thereafter, we have implemented reconfiguration with DGS placement then better reduction in all indices has noticed, therefore 2 more cases namely case 5 and 6 are considered. In case 5 reconfiguration with single DG by using PSO technique is implemented then the APL reduced by 71.59%, RPL reduced by 68.97%, and volt also decreased by 73.36% when it is compared with case 1. Multi-DG with reconfiguration by using PSO technique has implemented in case 6 and considerable reduction is observed in the multi-objective function where APL reduced by 78.60%, RPL reduced by 76.96%, and volt decreased by 82.28% hence their reliability is increased up to 96.65% as given in Table 2. After analyzing the obtained result it can be concluded that the optimal planning of multi-renewable distributed generator with reconfiguration using PSO technique is an effective approach to minimize the multi-objective based fitness function. Through this proposed work we achieved our target with 78.60% APL reduction and improved reliability of 96.65% along with better quality voltage profile as shown in Table 1 and 2 in all graphs. c://satish rao/pictures/project results/vol.png. In the comparison table, literature 1 and 14 presented optimal DG placement using MINELP technique and PSO technique of the IEEE 33 bus RDS respectively, whereas in 17 reconfiguration using PSO for the same has been carried. For the said cases in Table 3 the reduced active power losses are 72.95 kilowatts, 74.09 kilowatts, and 148.30 kilowatts, but in the proposed work of this paper the active power loss is reduced to 43.36 kilowatts. Also the voltage profile is improved with reference to the base case as given in Table I. 5. Conclusion. The optimal planning of DG with reconfiguration based on a multi-objective fitness function, which includes several system parameters using PSO, is evaluated on IEEE 33 bus RDS. Finally, network reconfiguration with multi-DG is implemented using PSO technique with MOFF. In the observed outcomes, APL, RPL, and volt are decreased by 78.60%, 76.96%, and 82.28% as shown in Table 1. Correspondingly, the overall reliability is enhanced up to 96.65% along with improved voltage profile as illustrated in result analysis with respect to the first case, i.e., with the base case. The outcomes are analyzed for different cases and also compared the results of finally implemented case, i.e., reconfiguration with multi-DG, case 6, with the existing work as illustrated in Table 3. It is concluded that the presented approach is effective for the decrease in apparent power. Therefore, the power losses, active and reactive, and the voltage deviation reduce significantly. Moreover, the system reliability and voltage profile of the system is enhanced.